السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Last lecture we covered the beginning or the basics of Perceptron training algorithm, right? So what is the main idea of Perceptron? The basic concept of Perceptron. Why we need a new learning algorithm? What distinguishes Perceptron from others? Yes, Abia? Yes, so the main idea is to give weights to the features. Okay, give weights to the features. So each feature will have a weight, and that will be considered as the importance of each feature. Okay, I think we stopped here at the end of last lecture when we started to talk about decision boundaries. Okay, we mentioned in that lecture that the points on the decision boundary will have dot product with the weight vector to be 0. So all points where the dot product with the weight vector will be 0 will actually constitute or will be considered on the decision boundary. That means that the decision boundary will be perpendicular to the weight vector. Okay, and we saw this I think last time. If this is the weight vector that we trained, then the decision boundary at any point is perpendicular to it. Okay, because at that time, on that decision boundary, the dot product is 0. Okay, and this is exactly the turning point between predicting positive label and predicting negative label. Okay, because if the dot product is positive, that means that the point is positive. If it's negative, then it means that the point is negative, or the predicted label is negative. So the decision boundary is the one that will separate both regions. Okay, and I think this is where we stopped last time. We said that the decision boundary will be a hyperplane. It will be a line in 2 dimensions, plane in 3 dimensions, and in general, a hyperplane. Right. Now, what happens in training? If this is the case, if the decision boundary always of Perceptron will be a hyperplane, then in training, we are trying to find the hyperplane that will separate the positive points from the negative points. Okay, so this is what the Perceptron training algorithm is trying to do, is to find the hyperplane that will do this separation. Okay, of course, it will be perfect if it will actually separate exactly the positive and the negative points. Right, this is what is happening in training. Of course, in training, we are changing this hyperplane, right? We are learning over time. We are trying to predict the label for the training examples. If we made mistakes, then we change the model, okay? But the objective of the training is to find that hyperplane. Right, what happens in testing? We check which side. Now we have a model trained. We check if, let's say that we have a point here. So we check, is it on the direction of course, with the dot product? Is it on the direction of the weight vector? If it's the case, then it is predicted as positive. If not, then it is predicted as negative. Okay, so we check the side of the hyperplane actually. We'll see a justification very soon. But that's what will happen in test. So in training, we are trying to find that hyperplane, but in test, خلاص, the hyperplane is fixed, which is the model that we trained, and we just check on which side the point is. On one side it will be positive, and the other side will be negative. Right. Now, let's think about what we mean by the dot product. The activation value is always a dot product, right? Assuming that the bias is 0. We assumed that last time. We start with the bias is 0. If the bias is 0, then the activation value is the dot product between the point and the weight vector. Let's think about what the dot product actually means. If we have the weight vector like that, then the decision boundary is perpendicular to it. We assume that this is the origin of the space. Then we have a point x. From linear algebra, we know that the dot product between W and X here is called the projection. Okay, so the value of the dot product is actually part of the weight vector, which is the projection of this vector, of x vector, on the w vector. Okay, so this is from linear algebra. The dot product means projection. So this will be now the projection of x on w. Fine. If that projection is positive, which means that the activation value is positive, then we should predict the label for it to be positive, right? So you will see that here the projection is positive. That means that x is on the same side of the decision boundary like w, right? Because the projection is positive. If x is on the other side, like this, then the projection will be negative. How do we know that the projection is positive or negative? If the projection is at the same direction of w, then this is positive. If it's on the right, on the reverse direction, then it is negative. Okay? When can we see that it is positive or negative? It is based on where it is from the decision boundary. So if the projection is positive, that means that x is on the same side of the decision boundary like w. They are at the same direction, the same side of the decision boundary. If x is negative, if x is on the other side, then the projection will be negative, and thus the predicted label for this point will be negative. Okay? So this is an interpretation of the dot product that we are doing, the activation value. If the activation value is positive, that means that the projection is positive, which means that the point and the weight vector are on the same side of the decision boundary. And that's why we predict the point to be positive. If the projection is negative, that means that the point is on the other side of the decision boundary, which means that it should be predicted as negative. Yes?
Doctor, if x is on the decision boundary, does that mean that this example doesn't have any?
That's a special case. That's a very special case. In this case, you can randomly choose whether it should be positive or negative. Actually, in the algorithm, it should be negative because the step function, if it's greater than 0, then it should be positive, otherwise it would be negative. Yes? What do you think? That's purely positive, right? That's purely positive. It's on the same direction, exact direction. Yeah, it's not just on the same side of the decision boundary, it's on the same direction of W. Okay, that's purely positive. Yes. Now we are assuming here that the bias is 0. Okay, we'll in a second we'll talk about that. Okay, any question about this? So this is now the interpretation of the dot product that we are doing. Okay, and how is that related to where the point is located, on which side? Okay, based on the weight vector. Right. Now we assume so far that the bias is 0. Let's think about what happens with the bias when the bias is not 0. Right. What are we doing with the bias? We add it to the projection, right? Right. Let's assume that the bias is positive. Let's assume that the bias is positive. In this case, when we have x like that, the projection is actually positive, right? We are adding to it the bias, which is also positive, so the activation value will be even more positive, right? So that means that the projection or the activation value will be even greater than the projection only, right? Type. So nothing new here. Type. What if we consider this example? So still this will be positive, right? Right. Let's see this example. Without the bias, the projection is negative, right? So this one will be predicted as negative. Type. If the bias is positive, let's say that this projection is -2, okay? And the bias is 3. That means that the projection plus the bias now is positive, which means that it should be predicted as positive. So the positive bias is allowing more space for positive examples. And now this without bias, that was negative. But with the bias, now it should be predicted as positive. So that means that we are increasing the area of the space of the positive examples. Okay? Which means that we are pushing this decision boundary in the reverse direction of W. It's like now the decision boundary is something like this. If B is 3, right? So this is now B. Okay? So we are allowing more examples to be positive. All examples in that side, of course, they will be positive, right? That's in the case that B is positive. Okay? All examples here will be positive. But we are also allowing that the examples that will be in that space will also be predicted as positive. That means that we are pushing the decision boundary to the reverse, in the reverse direction of W. Okay? Is that clear? Sorry? Yes. Okay. Right. We are adding the projection. So this is the activation value, right? The projection plus B. That means that the rule is that if A is greater than 0, then we will predict positive, right? Right. If we substitute A with projection plus B, this means that projection plus B greater than 0, that will give us positive, right? That means that projection greater than minus B means positive. So it was projection greater than 0. Now it is projection greater than minus B. So we are adding more possibility for the points to be positive. So we are pushing the decision boundary to the negative negative side. Okay, that was negative side actually. Okay, so the decision boundary now is like that. Of course, it depends on the value of B. Now, for a point that will be here, what will be the predicted label? Negative, because now the projection is much higher than the bias, right? But any point here, positive. Here, of course, positive. Okay? Right. That's if B is positive. What if B is negative? What happens if B is negative? Let's look at this case. Now, this projection is positive, right? Minus value, it will be even less, right? So if that new value is still positive, then it will be predicted as positive. If it's now negative, then it will be predicted as negative. That means that we are reducing the space of positive examples because now we are reducing the value of the projection. Okay? So now it is like pushing the decision boundary in the direction of W so that we can reduce the space for the positive examples. Okay? For the positive example. We are reducing the space for the positive examples. So in this case, so this is now the absolute value of B. Okay? Now, in this specific case, this is now the new decision boundary. Okay? Now X, the projection of X, let's say that this is 2 now, which means that B is minus 2. Okay? And this is 4. Still positive, right? But if we got a point here, the projection will be like 1, right? 1 minus 2 is negative. So now this point will be predicted as negative. So we are actually pushing the decision boundary in the direction of W so that we can reduce the space for the positive examples. We are increasing the possibility of negative examples when B is negative. Okay, is that clear? Any question about that? So this is the meaning of the bias. When the bias is 0, خلاص, it will be the origin. The decision boundary will be passing by the origin. If the bias is positive, we are pushing it towards, in the reverse direction of W. If the bias is negative, we are pushing it towards, in the direction of W. Okay? Is that clear? Any questions about this? Okay. Right. Now that we discussed the meaning of the dot product as a projection and also the effect of having the bias on the decision boundary, now let's see what happens when we do the update in the algorithm itself. Right? Last time we said that we will update the model when we make mistakes, right? And it was a specific formula. We add, we had something like this, right? W equals W plus YX, right? And Y is -1 or +1. Okay, and this is X. So we are even adding to the current model the vector X or subtracting it from the current model. Okay, now we need to know why we are doing that. What is the justification? What's the meaning of doing that? Okay. Right. We'll start with a positive example. Now remember that we are doing changes in the model only when we make mistakes, right? Only when we make a mistake. Right. Let's assume that this is the current weight vector, which means that the decision boundary is perpendicular to it, right? So that's the decision boundary. Now, while we are training, we got this example. This example is actually positive. The actual label for it is positive. What will be the predicted label? How did we know that it's negative? It's on the other direction, right? In the other, on the other side of the weight vector, right? So it should be predicted as negative, which means that the model now is making a mistake. And this is a misclassification, right? Right. When we have a misclassification with positive example, remember that was YX, right? Y for a positive example is +1. So we are actually adding X to the current model. Now let's see what does that mean. We have the W old, which is the original weight vector, and this is X, right? This is X. Now, how do we do the addition of vectors? If I have a vector like that, A, and I have another vector like that, B, what will be A plus B? Yeah, at the end of that vector, we add another one that is parallel to B, right? And then we have A plus B. So that will be A plus B, right? Now, that's in linear algebra. Here, we do the same thing. This is W old, and we want to add to it X. So this is X parallel to that, and then this will be W plus X, right? Which you see here in green. Okay, so that's W old. When we added X, this is W new now. Of course, we changed the weight vector, right? So the decision boundary will change also. So now the green one is the new decision boundary. Okay? If you look now at that point, it was predicted as negative here, right? What will happen after we add X? Now it's positive, right? Because now W changed a lot. Now W and X are on the same side. So it will be positive. So you see now that's that update. What happens is that we pushed W towards X because we added X to it. So when we push W towards X, most probably it will be on the same side. Now because we changed the decision boundary, now they will be on the same side, which means that if we, at that moment, if we check again, or if we predict again the label for the example that we just misclassified, it will be correctly classified. Okay, so this is the interpretation in case of a positive example. Any questions? Is that clear? So with positive example, we misclassified, right? So we should go close to it. That's the idea. So we add x so that the new w, you see here, this is the old w, it's far from x. Now we pushed it towards x. So now x will be considered positive with the new model. Okay? طيب, what will happen when we have a negative example? Misclassified, of course, right? Now we don't change the model at all unless we do a mistake, right? So for this example, with this model, what will be the predicted value, predicted label? Positive, of course, right? Because that's now x. The projection of x on w is positive, right? So, and they are, of course, on the same side, so it is positive. But it is actually negative. So we'll have to update the model to push it away from x. So that's why we actually subtract x. If you look at the algorithm, you will see that y is not a negative 1. In this case, we are adding yx, right? So it will be like subtracting x. So this is w, this is x, right? So this is minus x. It's like adding minus x, right? So it's minus x, so the new w will be like this, right? This is w plus minus x, this is w minus x. So this is now the new weight vector. Now if we predict again, what will happen? We pushed w away from x. Okay, you see here now, this is the w, the new w, this is the new decision boundary. Based on that, what will be the predicted value for x? Where is x? This one, right? This is x. So based on the new model, this will be predicted as negative. Okay? Is that clear? Following with me? Any questions? So that's the justification of the algorithm. That's why exactly we are doing dot product. We are adding or subtracting the examples, right? And the meaning of the decision boundary and the meaning of the bias. So all the geometric justification of what we saw last time. Yes.
The last lecture you talked about the threshold.
Which threshold?
I don't remember.
You mean the maximum iterations? The hyperparameter? What's the threshold?
There was a slide about threshold, and I asked you if it's the same as the bias, and you told me it's not.
I don't remember what we mean by threshold here. But if we are talking about the activation value, then yes, the bias will be considered as a threshold, minus the bias actually, as we said in the previous slide, right? So because we have wx plus b, that has to be greater than 0, right? So that means that wx has to be greater than minus b. So you can consider minus b now to be the threshold for activation. If that's what you mean, I don't remember actually. Any other questions? Right. Now we are done with the justification. We just now see Perceptron as we did before with as a function approximation. Remember that we discussed it before, right? That we can see any machine learning problem, classification problem in particular, as a function approximation. Right. What is the setup here? We have, again, as we did in KNN, we have all possible instances in the space are feature vectors. The target function here is between two values. It's binary, right? We assume here that this is binary classification, so the target function is binary valued, is either -1 or 1. Now, what is the set of function hypotheses? The set of function hypotheses is a set of possible models. Okay? In Perceptron, what are the models? Are hyperplanes, right? We mentioned that in training we are trying to find the hyperplane that separates the positive from the negative examples, right? So the space of solutions here, or the space of models, are all possible hyperplanes. We are trying to find one that will separate the positive and negative examples. So each hypothesis in that set is a hyperplane. And the input and the output are the same like before. We have training examples, and the output will be one hypothesis that hopefully will be a good approximation to the target function that we don't know. Okay, any questions so far? What are the hyperparameters in Perceptron? The maximum iteration only. The bias is not a hyperparameter. What is the bias? The bias is a parameter or a hyperparameter or a constant or what? What do you think? How can we know whether it's a parameter or a hyperparameter or anything? Okay, type. The bias controls the other parameters? Type. Can we consider the bias as a parameter? How can we know if it's a parameter actually or not? Very good. Using the learning algorithm, right? Is B learned from the learning algorithm, using the learning algorithm going through the training examples? If you go back to the last lecture, you will see in the algorithm that we update W and B. Both are the model, right? The weights and the bias. So bias is learned from the training data, which means that it is a parameter. Okay? Back to your question. What is the benefit now for the development set is to tune the hyperparameters. So the question now is, what is the hyperparameter that we have here, which I think was answered by the maximum iteration. What is the maximum iteration? How many times we go through the training set. I think now you have an idea why we are going through the training set multiple times, right? Because we wanna train, the model to learn from the mistakes. Okay, so in one iteration, it might not see all, learn a lot from all the examples. So we'll have to go through multiple iterations until we are done with the number of iterations. How can we get the best value for the maximum iteration? Tuning. Okay. How? Using the diff set. Okay. How? Yes?
Choosing different maximum iterations and training depending on those, and then seeing the best results and picking
on the diff set. Yes, exactly. Let me show you. I think we are. Okay, quickly I will show you quickly. So let's do it on that slide because we have more space here. How can you tune the maximum iteration? Here you do a plot like that. This is number of iterations, and that's, let's say, accuracy. Okay, so we have here 1. When we have maximum iteration to be 1, that means that we'll go through the training examples just once. Let's say that the accuracy was like this. Okay, now we increase the number of iterations. Will we learn a new model when we increase the number of iterations? Yes, of course, right? So we'll have another model. We compute the accuracy of that model. Let's say that we got it here. Accuracy on what? On which set? No, this is diff set. Okay, so that's accuracy on diff set. Then we try 3. Say we got it this way. We try 4. We got it here. So you see, something like this will happen. This is on div. If this is the case, then what is the best value of the maximum iteration? 3, because that's the maximum. If we draw this but on training set, what would you expect? Yes, it will be increasing probably like this. And we saw this plot before, right? Something like this. So on training, we expect that it will, of course, be better over time, but we don't know if it will generalize or not. How can we test the generalizability of the model on the data set? Okay? Is that clear now? Now let's, in the last 5 minutes, let's talk about some practical considerations of the Perceptron algorithm. So far we discussed the standard Perceptron algorithm. The first issue is that the order of training examples matters. Let me give you an example to show you this. Let's say that we have 200 examples in the training set. The first 100 was all positive, and then the second 100 was all negative. Now the Perceptron algorithm will go through them one by one, right? So it will see the positive examples, maybe the first 5, 6, 7, it will make mistakes, and then all of them are positive, right? So it will start to think that everything is positive in this world. Okay, so it will be fixed. So it will not learn from all the positive examples. Maybe it will learn from the first 5 or 6, and then will be fixed. Then when it comes to the next half, it will start to see negative points, right? So it will start to change, maybe for a few examples, and then again, because all of them coming are negative, it will probably be fixed. So overall, it didn't learn much from all examples. It learned from few positive and few negative. That means that the order, of course, matters, the order of examples. Because with every example, we might change the model, right? So the order of seeing the examples will affect the changing of the model. Okay? So the idea here is that maybe better to make sure that this specific case doesn't happen is to randomly permute or order the training examples. So we don't have all positive and then all negative. We would have kind of mix, okay, positive and then negative and so on. So mix of positive and negative examples in order. Okay, so doing a random order is much better than just getting the or going through the examples as we get them. Right. The question is, where should we do that? Remember, in Perceptron, we had 2 nested loops, right? One with maximum iterations, going through all the data number of times, and then the inner will go through the data once, right? Where should we do this random permutations? We call this shuffling, by the way. Shuffling means randomly ordering the training examples. Where should we do this shuffling? Should we do it before the outer loop? Should we do it once in the beginning and then? What happens if we do it just outside the outer loop? That means that we'll do it once, right? Then in every pass on the data, it will be in the same order, right? Better than that is to do it in the beginning of each pass on the data, which means that it should be right before every iteration or actually in the beginning of every pass on the data set, on the training set. Okay, so every iteration of the outer loop, we do permutation, then we go through the data. Then we do, shuffling. We do shuffling again, and then we go through the data. So, which means that every pass, the Perceptron will go through the examples in different order. So there is a more chance to learn from the data. Okay? Did you got this point? Okay. Right. Another one is what we call early stopping. We should not increase the maximum iterations a lot. Okay? And we can control that by what we saw in the previous slide, right? This plot, we can tune it based on a div set. This is called early stopping. We should not make so many iterations to avoid overfitting. So this is what we mean by early stopping. And the last one that we will, inshallah, talk about it more in the next lecture is that maybe something that you noticed with the algorithm. Whenever we make a mistake, whenever the model makes a mistake, we do a change, right? Right. that means that we changed the model that was before, which means that even the decisions that we would have made on the previous examples, it might change. So sometimes simple modifications with one example, that the model might change dramatically and might affect the performance on the previous examples. Okay? But we actually changed the model and we don't have any record of the previous models. We just changed the model because of one mistake. Okay? So we will, inshallah, see next lecture how we can deal with that. The main idea is to keep track of the previous models. Some of them were actually good enough to be used. We don't have to just keep the last model. The vanilla Perceptron so far makes changes, and we keep just the last model, right, with the last change. That might affect severely the predictions on the previous example. So we'll see, inshallah, next time how we can deal with that.